Hello, everyone. Welcome to today's class, where we'll be looking at the Fundamental Theorems of Calculus, FTC Parts 1 and 2. So the Fundamental Theorems of Calculus serve as a bridge in general between differential calculus and integral calculus. So we know there are two parts to really, when you start to look at calculus, the differential calculus side and the integral calculus side. Now, there are two parts. So the FTC part 1 is where we're going to start from today. So the fundamental theorem of calculus, the first part says, suppose that f is a continuous function on the closed interval from a going to b, and is also differentiable on the open interval from a to b, that is without the endpoints a and b. And if x is a variable that lies between a and b, then we have this conclusion. If we can write this integral from a to x of f of t dt as a function of x. So this is dependent on x because a is a constant and g of x is this integral, which is a function of x. Then the derivative of this function with respect to x is exactly the function f of x. In other words, if you have this integral, g of x starts from a, you're going to a point x, and then you're taking this integral of f of t with respect to t. We're saying it really just depends on x. And when you take the derivative, it's literally that function, but replace your t with x. Okay, so let's look at a picture that kind of illustrates this for us. So we can think about this integral here as the area so far under a curve. So we're given this curve y equals f of t, and then we're looking at the area from, remember, we're looking within the closed interval a to b. And so our area is g of x, which is the area so far. So x is like a variable that's kind of, you can move it forward or backward. So this is the area that has been covered so far under this curve. Okay, so if we want to look at an intuitive justification, because we're interested not just in using this as a formula to solve problems, but to really see what's the reasoning behind this result. So if you look at this, what you realize is that we can consider g of x plus h. So we want to build up to the derivative using the limit definition. So we can consider g of x plus h minus g of x as an area. So if you think about it this way, you've got journeyed up until g of x at this point. And then if you move just a little more distance here, and let's say this point is x plus h, you get this. You get that your entire area up until this point will be, so if I added this, that area, all of that will be g of x plus h. Okay, what does that mean? I can look at what happens within a little rectangular strip under the curve. Okay, so if I'm just concerned between what happens between x and x plus h, which is just a little strip under the curve, then that looks like a rectangle. And we know how to find the area of a rectangle. So you can see that g of x plus h, which is the area up until x plus h, minus g of x, which is the area up until x, which we had before, gives you this small portion that we can see here in this picture. Okay, what does that mean? Well, we know that this is approximately h times f of x. Okay, this is approximately the product of the distance between x and x plus h, which is h, and the height. We're assuming we consider the point where you touch the curve, which is at f of x. Okay, and so what we have is that the difference between g of x plus h and g of x is this small area of this rectangle, which is given by length times breadth, which is f of x times h, approximate. Okay, so the intuition here is that if you divide both sides by h, then this is your difference quotient. And as you take the limit as h goes to 0, that is our derivative, g prime of x. But from what we just said, that is exactly f of x. And so that's the intuitive justification. Of course, the proof is more elaborate than that, but we just want to give kind of like a picture and of what this essentially looks like. Okay. So that being said, there's a second part of the fundamental theorem of calculus. So this is the first part. Let's look at the second part. The second part says, if f is a continuous function on the closed interval a to b, and f of t is the derivative is g prime of t. In other words, if g is an antiderivative of f, then this integral from a to b of f of t dt is exactly g of b minus g of a. Okay, so what is this saying? This is an interesting result. So if you go back just up to this picture, we had the first picture. We're essentially saying that this area under the curve, so if you consider everything from a to b, this has to do with, you know, the area under the curve, which kind of takes into account all of the values as you go across from a to b. However, what the FTC part 2 is saying is that to get the integral from the beginning to the end point, we do not need anything other than just the two evaluation of the antiderivative at the beginning point and at the end point. And so that's a really interesting result. So essentially, you just say g at the end point minus g at the initial point. Okay, so that's really what it is. So let me try to, let's try to give an intuitive definition here or justification of the Fundamental Theorem of Calculus part 2. But before that, I want to talk about, you know, this integral. What does this mean? So whenever we see this integral, we can talk about it as the Riemann integral. So what does that mean? Well, it's the area under the graph, which is really the picture we talked about earlier above here. So we can look at the definite integral as a Riemann sum, which is, remember we divided this into, you know, we had this small rectangle. So really, we can divide this area into several rectangles if you wanted. So we can have something that looks like this, let's say, you know, like this, and just like a bunch of rectangles, and you can continue that way. So we can divide this into rectangles. Why do we do that? Because we know how to find the area of rectangles. Okay, so if you look at that, and if we look at, maybe you can use either the start point or you can use the end point, but let's just use the start point in this case. Okay, so if you look at this, what you have is that each of those areas kind of give you, when you sum it up, gives you an approximation for the area under the curve. Okay, now notice that if I refine this by adding more rectangles in there, okay, then I would get an even better approximation. So if I added this and I made this smaller, you see that I kind of close up the gaps, and then I have a closer approximation. And the more I do that, the more I get very close. And so that's why that is a limit problem. So that gives us, so that's what we have here, that the integral, the area under the graph from A to B is exactly the limit of each of the, you know, the rectangle sums, the area of the rectangles. When you take the product of, when you take the sum of the areas of all of those rectangles and you sum that up, okay, then you get an approximation. And as you take the limit of your delta t, that is the change that we have in each of those rectangles, so the width of the rectangles, as you make it smaller, you get something that gets very close to that area. So that's what essentially the Riemann sum is. So I hope that is clear. Okay, so we call that expression the definite integral, of f of t from A to B. That is the actual area. Okay, so let's talk about a justification of the fundamental theorem of calculus part 2. So first is that we assume that we have two functions, capital F and small f, such that capital F prime is equal to small f. Okay, now remember that the definition of derivative, we just talked about that earlier. The limit definition is given by f, capital F prime of t is the limit of this difference quotient. Okay. Now, if you look at this top, the top here is pretty much delta f. It's change in f. Okay. So this is your delta f, if you will. And so you can kind of cross multiply here or multiply both sides by delta t. And so you have f prime delta t is approximately delta f, okay, because it's a limit. So this is what we have. Now, what does that mean? It means that if this is what we want to evaluate, so we start here, but we said this is exactly given by this formula, right? The Riemann sum, which is the limit. But each of these, you can replace ft delta t, because remember, capital F prime is equal to small f. So ft delta t is the same thing as capital F prime t times delta t. But by this approximation, we have that this is approximately the limit as delta t goes to 0 of this sum of the delta f's. So essentially, you are saying something like f of your initial point. So for instance, if we divide this into a partition, so a partition essentially says you have a set of terms between A and B. So A, let's call that A, then the next one we'll call it T1, the next one we'll call T2, and so on. So let's say up until Tn minus 1. Okay, Tn minus 1, and then the last one, let's call it B. So this is a partition because it divides the interval into sub-intervals. What does this mean? Well, if you're taking delta f from t going from A to B, you have f of t1 minus f at A, which is really what you're doing here. F of t plus some movement minus the previous one. So this is what you have, plus, and then you add that to f of t2 minus f of t1. Okay, and so on. And you kind of continue that way until you get to the last term here, which will be f of b minus f of t sub n minus 1. So that's what we have. Okay, what can we do? Notice that t1 and cancels, f of t1 is canceled out here. F of t2 will be canceled out, and so on. And it will continue until we get to the last one. F of t sub n minus 1 will be canceled out. And we will be left with f of b minus f of a, which is really how we get this part. So that's an intuitive picture of what is happening here. Again, this is not the full proof, but it gives us an intuition. Excuse me. So we're adding up all of the changes in f, and that's what gives us this. So this is kind of the picture for the first theorem of the fundamental theorem of calculus, part 1 and part 2. Okay, so I want to go ahead and just look at a few questions that would help us to understand what we've just looked at. So, but before I say that, just a few comments here. Now, antiderivatives, if f, capital F prime is equal to small f, we say capital F is an antiderivative of f. And the other thing is that if you have two antiderivatives, then both of them differ by a constant. Okay, so if capital F and G are both antiderivatives, then f minus G is a constant. And the integral without any limits from A to B is called the family of antiderivatives of f. Okay, so like I promised, I want to look at a few examples here just to see some of the things we've learned. So the first question is we want to find the area under the parabola y equals x squared from 0 to 1. So let's do this. How do we find this area? Remember we said that the area under the curve is given as the integral from a to b of f of x dx. Okay. And so we can, our f of x in this case is y, which is x squared. Our a is 0 and our b is 1. So if you plug that in here, you have the integral going from 0 to 1 of x squared dx. Okay, so what's the antiderivative of x squared? We know that an antiderivative of x squared is x cubed over 3, because when you differentiate this, you have 3x squared over 3, which is x squared. So this is an antiderivative. Okay. And if you want, you can add a plus c and take from 0 to 1, but the c's will cancel out. So, but let's see. So we have remember that by the Fundamental Theorem of Calculus, part 2, you just need to evaluate this at the 2 endpoints and subtract. So this is 1 cubed over 3 minus 0 cubed over 3, which is just 1 over 3. And that's what we have. That's the area. So here we use the FTC part 2. Okay, let's do the second one. We want to find the derivative of the function h of x going from 0, which is the integral from 0 to x of the square root of 1 plus t squared dt. So that immediately tells us we need to use the Fundamental Theorem of Calculus part 1, right? So use FTC part 1. Okay, so how do we do that? Because this is our h of x is this integral, h prime of x will be whatever function we'll have here. However, you have to replace t with x. So this is square root of 1 plus x squared. And we're done. So that is the derivative we're looking for. Okay. All right. We have one more problem we want to look at and we'll be done. Okay, so we want to find the derivative of this integral. However, we need to be a little bit careful here because you can see that this is not x, but this is x cubed. So that means some sort of chain rule thing comes in here. So let's start by saying, let g of x be equal to the integral from 1 to x cubed cosine t dt. So we want to find g prime of x. That's true. Okay, so what do we do? So to find g prime of x, notice that what we want is if we replace u, so we say let u be equal to x cubed. So what we now have, let me rewrite this. So what we have is going to be g at u is integral from 1 to u of cosine t dt. Okay, so by the chain rule, we have g, or let me write it this way. The g dx is going to be the g du times the u dx. Okay, good. So the g du we know is going to be by the FTC part 1. So let me write FTC part 1 tells us that the g du is just going to be cosine of u. And then you're multiplying that by the u dx, which we know is going to be 3x squared. So we multiply that, 3x squared. And now we can just finish up what we have here. So what is our u? Our u is x cubed. So this is 3x squared cosine of u, which is x cubed. And we're done. So here we have used both the chain rule and the FTC part 1. So this is an example, these are just a few examples of how we can apply the fundamental theorem of calculus in proving or in solving problems that show up in integral calculus, so finding the area under a curve and so on and so forth. Okay, thank you for listening. And if you have any questions, I'll be glad to definitely look at any questions you might have.